Is this good?
Yeah, it's showing up. Yeah.
Okay.
It's good.
Thank you so much for inviting me, Krishna, and thank you everybody for attending it. I particularly like the series. I think this is a great service to the profession. I liked it, and I really appreciate it. Today's topic is, as Dr. Reddy mentioned, compost reuse in geoenvironmental applications. So what I'm going to do is I'm going to cover material from several projects we have on compost reuse. We have finished and almost finishing 4 projects, and we have another 2 projects in the pipeline on related to compost reuse. So what I will do is I will mention the definition of the compost, and I will provide geotechnical properties of compost, in one of which we accomplished in one of the projects, and then later on I will focus on other issues related to compost reuse. Compost is a controlled aerobic biological. Compost is a, first of all, industrial byproduct. It is under the category of recycled materials that many of us are interested in, and it is produced as a result of biological decomposition of organic waste material under controlled aerobic conditions. That waste materials have been many. You heard the term compost. I'm sure maybe the most common one is food compost. We have heard terms such as biosolids compost, which basically comes from sewage sludge or wastewater treatment facilities, to be more proper. Sometimes we heard the term leaf compost, green waste compost, and they typically come from the garden waste, like yard trimmings, leaves, manure. There's also mushroom compost, and so on and so forth. Among many of these composts, we had focused on the ones that are common to our location, and as well as the ones that are more commonly used or have the potential to be used by the different highway agencies or by different government agencies or local agencies in the region. Approximately 30% of the municipal solid waste generated in the US is compostable, and that of course includes the composts, different types of compost that I mentioned. We are in Washington, D.C. area, nation's capital, and that little TERP sign shows where University of Maryland is located. And Chesapeake Bay is of interest to us because Chesapeake Bay is the largest estuary in the United States, and there are several laws that protect the Chesapeake Bay at the local level as well as at the national level. And because of that, there is a lot of interest on the impaired body, and then the total amount of total loading basically, or contaminant loading into the Chesapeake Bay area has been interest to several agencies. And as I mentioned of that, there's a lot of different guidelines related to that. So that kind of interested us going after this project. Number one, compost has been deposited at different locations and people are looking for reuse. And on the other hand, there has been interest in using compost, but there has been several documented studies that go against the use of compost. Because of that, and being in this region, we were encouraged to go after this research by several different agencies, and that's how we were funded. The first topic is, I know that there are several geotechnical professionals in the attending the seminar, so I wanted to give an insight of the geotechnical properties of these materials used in geoenvironmental applications or in applications in general. And among those applications, highway systems have been very interesting because, as you are very well aware of, recycled materials are more commonly used in highway systems. The main reason for that is we have kilometers of highways, right? Miles and miles of highways, in the US as well as other places. And then there is always rehabilitation of these highways. And in addition to that, they're building new highways. And there are county roads, there are local roads, and so on and so forth. Therefore, there's a lot of interest. And when we say highway systems, it's not necessarily the payment system that we are interested in. That's, there's basically the base and this sometimes the stabilization of the subgrade underneath. And along the highways, there are stormwater systems, bioretention systems, we have retaining walls, and you name it. And that's why potential use of recycled materials in highway systems has received a lot of interest. In regard to the compost is very rich in organic material and rich in nutrients, and that's why it promotes the vegetation. What's typically used as a vegetative growth layer on highway slopes is a material called topsoil. Topsoil is, again, rich in organic materials, and the question here is, can we replace the topsoil with some type of compost or topsoil compost blends so that we could achieve the same performance? Among those, you can see the pictures of different materials for your information. Topsoil looks like very similar to a sandy or sandy silty soil, but typically more on the sandy side. And biosolids compost is, again, here. You can see it. There are lots of fragments in it, including a lot of fibrous elements and very rich in organic material. Again, I'm going to give you some of the properties of these materials in the slides. And you can see the green waste compost that comes in different names. One common name is leaf compost, but that doesn't necessarily mean that it originates from leaf. It could be including yard trimmings. There's also mulch compost that is a little bit different, but the one that we focus on in this case was the leaf compost. If you look at the local jurisdiction, it requires you to look at a textural analysis. Let me actually maybe go one by one so it kind of helps. Look at the textural analysis, and textural analysis here is nothing but grain size distribution. There are different names in this design system or in this engineering, and then the term that we use commonly, grain size distribution, coincides with the textural analysis. In the textural analysis, they typically use the USDA, United States Department of Agriculture system, for obvious reasons. Then we look at if it meets the specification. SHA here is the Maryland State Highway Administration. So again, we are looking at the local, one may be looking at the more national level, but in the US especially, we typically look at the state level specifications. So that in that case, state highway is the one that applies to us. Then if it does, then we basically can add more compost, but we also have to make sure that the textural analysis requirements are met. Then if no, then we add more topsoil. So what we are trying to here do is look at the textural analysis. On top of that, pH and organic matter has certain requirements. Obviously, by adding compost, we will be increasing the organic matter content significantly. So that kind of goes outside of the specifications, and the local agencies are aware of that. But the pH requirement is important. pH remaining, like neutral pH is remaining anywhere from like 6.5 to 7.5 is highly recommended for this region. And I could imagine that it could be for other regions. Of course, it depends on the availability of surface waters and groundwaters, and pH effects on these two types of water bodies will obviously be different. And we use different types of materials. I'll try to be consistent with the legend here, and if I'm not, then I will certainly clarify. Topsoil, for instance, will be T. And then we use, as I said, biosolids compost, and then you can follow these legends on the slides. There's no need to read. And we also use blends. For instance, if you use what's called a TB1 blend, that would include 85% topsoil and 15% biosolids compost. This is by weight, by dry weight. Of course, in the field, they mix it by volume, and I will give you some indication of these volumes too. But just to be on the safe side, if I tell you what 85% by weight topsoil and 15% biosolids compost mean, that would roughly be around like maybe 2.5 to 1 ratio of compost to topsoil. So compost, again, has very low weight, very low specific gravity, but by volume, it will be higher. So even though the by weight percentage is low for the compost, the by volume compost, by volume percentage will be, or by volume ratio will be much higher than that of topsoil. And you can see the other ratios as well. Okay, one thing here is looking at the compaction properties. We don't perform the same compaction like we do in other soils, in other systems, such as subgrades and bases. However, it's important to know how the water density relationships of these materials differ from topsoil, just for our own purposes. Here you can see the red one all the way at the top is the topsoil. And then all the way at the bottom, you can see these two. I'm not sure if you can see my cursor. Here, these, the ones at the bottom, the green waste, as well as bio solids compost. And somewhere in between, you can see the blends. You can clearly see that once we add compost, it decreases the dry unit weight. Just for an example, if you are building an embankment in Maryland, you typically look at about 95 to 97% of the either the modified or standard Proctor compaction. But also, as a rule of thumb, they need a minimum unit weight of about like 15.5, 15.7 kilonewton per cubic meter. That kind of corresponds to that unit weight. So topsoil, yes, we are not building an embankment with the topsoil, but that kind of, exceeds or meets that requirement, versus the other ones are way below that. So when they compact these systems in the field, they don't really apply any type of compaction forces. They apply a little bit like tamping forces. So they locate the particles in it, but with the intrusion of the different type of construction equipment and the vibrations produced by them, the soil is inevitably compacted to a certain degree. And that was very evident from the compost blends that we collected from different types of applications. Example, here you can clearly see that the unit weight is around 7s, right, for this compost. When we collected field samples, they were around like 13 because of the construction in the region, that was compacted inevitably, or at least unexpectedly, by these nearby equipment. If you look at the grain size distribution of these materials, topsoil is right at the top, and then once you add the compost, it makes it coarser, and same is true for the leaf compost as well. So you are basically achieving a material with a coarser nature, and you can imagine how it will change its direct shear, frictional properties as well as hydraulic properties. And that's what we wanted to test as well. We ran some direct shear tests under varying normal stresses. Sometimes we went very high, but much higher than what you would see under these type of applications. You can imagine that the normal stresses would be low at the superficial applications. We also ran some triaxial compression tests just to show how the pore pressure regime will be affected around these systems. And you can see the direct shear results, typical friction angles for the topsoil around 34s with a very low cohesion. And then when you look at the blends, the friction angle jumps significantly, and almost no cohesion is left. And same is true for the triaxial systems. Now you can see the total as well as effective friction angles, and then the cohesion, a little bit cohesion present inside the topsoil. Then when you go to the blends, the friction angles also differ. We recognize that these materials are different than other type of textbook soils or natural earthen materials, whatever you want to call that. We said, well, can we look at the fibrous nature of the soil under the an imaging system, and capture some images and try to quantify them and relate that to frictional properties. We have this aggregate image measurement system. in our laboratories captures two-dimensional images by using the a camera system. There's a tray that rotates, and then you can capture images consecutively from different angles. And then basically the software, by using the imaging tools, it combines those different images and then comes up with a pseudo three-dimensional image, and then measures the different properties. Without going into the details of this system, which could be found in different publications, here the different particle ranges used to analyze different type of shape parameters are listed. Example, if you want to measure the angularity, these are the ranges that you should be including in your these are the ranges of soil particles that you should be including in your setup. If you are measuring an elongation, which is termed as form 2D, then you should be including these ranges of particles, and so on and so forth. They are all listed here. So there are scales commonly used by others in the past, and you have seen these, you know, in very old publications even. And before the development of image-based systems, we used to use them, but they are still very useful, and they are good check against image-based systems, and we did that. And the comparison of the image-based values for, let's say, for angularity going all the way up to 2000, which indicates rounded particles corresponding to a Crumbine scale of 0.6 is given in the first image, and so on and so forth. So those type of scales can again be used. Same thing for the elongation. You know, you can use these type of charts. So we did the both just to be on the safe side, making sure that our imaging approach is working fine, and it was. For instance, you can see here the angularity range, and then how it affects the friction angle for different type of particles. Again, you can see the topsoil at the bottom, and then the compost is at the top. Obviously, we were in this case we were right, and it was obvious that there were fibrous elements inside the blend that was increasing the friction angle, and then same is true for the leaf compost. And if you look at the, for instance, elongation, you can see the same things. You have more elongated, and as you have seen in the earlier slide, more angular particles with the inclusion of the compost, which basically tells us that this was the main reason for increasing the friction angle. Hydraulic conductivity tests were conducted. Obviously, we compacted them in the flex wall permeameters. That's why we have lower permeabilities than what you would see in the field. Example, for a topsoil, if you don't compact them to those degrees, then you would have about 2 orders of magnitude higher K in other systems. Example is you can use bubble tube permeameters. They would give you falling, you can run falling head tests as well as constant head tests depending on the K of the soil in those permeameters. And then the important finding here is, again, with the inclusion of the compost, there's a significant change in the hydraulic conductivity. We looked at the unsat properties, unsaturated hydraulic properties of these systems, because they're superficial systems, and plant growth is important. So it's very related to unsaturated properties. We are using a very recent system called Hyprop system, developed by Meter Group in the US, and using a simplified evaporation method. And then it goes up to 100 kilopascal suction range. Now they modify the system, and it can go up to 2,000 or 3,000 kPa suction range. So I'm excited about that new system. And it requires the back saturation prior to testing. And there are tensiometers in these systems, obviously measure suction at different levels. So what do we really get from this is, many of you are aware of the soil water characteristic curves, relationship between volumetric water content and metric suction. So we typically determine what's called a field capacity, and then later on a wilting capacity at the recommended metric suctions of 10 and 1500 kilopascal respectively. And then at these levels, we can determine the filled water content or wilting water content at the wilting point, shown with the theta values on the y-axis, and anywhere between the difference between the water contents determined at the field capacity and wilting points is called, available water content. And that available water content term is very important for plant growth. Van Genuten equations or Moallem equations coupled with the Van Genuten ones can be used to provide best fits to these data points in the lab. And then we did that because we were limited to 100 kilopascal. Typically 100 kilopascal would be fine for us, but if you want to get the full curve, then you can also have these predicted values. So basically, these are the laboratory measurements. These are coming from the best fit from the Van Genuten Moallem equations. And then what you see here is the topsoil provides you the soil water characteristic curves at the bottom. And then any type of compost addition would shift the curve upwards. What you see here is the compost treatment increase the plant available water content, which is the AWC that you have seen in the earlier slide of the topsoil by 1.4 to 2.6 times. That was again a beneficial thing for the compost. You can see the hydraulic conductivity metric suction curves here, and that again shows the fill capacity and wilting points one more time. You can see the red line, which is the topsoil at the top, and then once you add compost, you can clearly see that there was a 1 to 3 orders of decrease in the unsaturated hydraulic conductivity throughout the drying process, and decrease in the K value hydraulic conductivity during this drying was the sharpest on compost due to their high porosity and tortuosity. And I will give you some porosity values later on too. So this is a list of the available water contents you can see on the right. If you want to examine the field points and wilting points, you're welcome to do so as well. Here, the available water content, as I said, increased significantly. For instance, for topsoil, it was around 11. And then for blends, it jumped up to 14 to 25, ranging from 14 to 25 roughly. And for pure compost, obviously, it will be much higher. An interesting point here is the wilting point. You can look at the wilting point for the pure compost. It's extremely high, much higher than what we would see for a range of earthen materials. If you look at sandy soils, they're around like 20s, maybe 18, 20, 25 in that region. And for the compost, it's almost doubled. Conclusion from the first study that we finished, we figured out that the shear strength of the topsoil increases by compost treatment. And that was more obvious if we increase the normal stresses. For us, the superficial application would require low stresses, obviously. K-saturated value was strongly correlated with compost content. I did not show you everything here. They could be found in the publication that I cited. And for instance, the gravel content, sand content, fines content, like particle size of the compost, obviously affected these saturated values. Again, we are using the term like gravel content here. If you look at the United States Department of Agriculture chart, they would not use that. So if one wants to follow strictly the USDA chart, then those terms can be modified as well. I was directly following the unified soil classification system. Compost amendment increased the available water content of the topsoil, which is very important for plant growth. And also the biosolids and leaf compost treatments decrease the K values in unsaturated zone for about 1 to 3 orders of magnitude. The second study that we looked at was compost for sediment control and vegetation establishment in highway systems. Soil, so we have to be, we were looking at the soil erosion in our applications, and soil erosion is a major environmental challenge, and that encouraged us to look at this problem. And conventional practices use straw matting, silt fence, turf grass, and there's increasing, as I said, use of increased interest in using renewable materials. Compost is one of them. So it could help to improve the aggregation and reducing the bulk density. I'll give you some slides on that. And I mentioned the benefits of compost and before, so no need to repeat them again. We want to balance the desire for rapid vegetation establishment. That's our main objective here. So we work with, I have still been working for the last few years with plant scientists and soil scientists and environmental engineers. I'm myself as a geotechnical engineer by background. So one of the objectives here is the vegetation establishment. Another desire is the improved infiltration and rainfall retention, right? And because we are interested in limiting the runoff, right, in these type of systems, slope systems or highway systems. And however, one concern that I did not mention as part of the first study, which focused on the geotechnical properties only, is the nutrient leaching. Yes, the nutrients are good, like phosphorus and nitrogen, but significant, and also potassium to a certain degree. But the problem with the compost is significant, so that has to be addressed. So we wanted to look at the compost amendment, and then we wanted to look at if lacking of the chemical fertilizers, which you use with the topsoil application, by the way, which you wouldn't need it for the compost, it could be an advantage. And we also, to a certain degree with luck, and then to a certain degree with the suggestions of the local highway agency, inclusion of the straw in these systems, how it would affect. Okay, we looked at different things. One of them is the measuring the ground coverage in a quantifiable and consistent way was very, very important. Okay, this grass grows or the plants grow, but can we quantify them in real time? So we developed an algorithm that use computer vision tools, and we coupled that with AI, and then we artificial intelligence, machine learning systems, so that we can optimize the coverage to perform quickly and reliably. Second task was observation of these systems, observation of their performance in the field and greenhouse applications, namely vegetative growth and then runoff quantity and quality, and then develop a baseline for compost addition. And then later on, looking at different effects such as slope ratio, straw mulching, different type of percentages of compost to topsoil. Let me look at the image-based system first. I already mentioned the objectives in the earlier slide, but one thing we did is once we trained this algorithm, we used the different type of imaging tools. We heavily relied on MATLAB imaging tools, and then we also trained the algorithm. And then once it's trained, we were comfortable that it was giving us the right values. We did image segmentation as part of MATLAB tools. And then we also had to find different thresholding values for different type of fragments inside the compost systems, because now we have soil, now we have straw, now we have grass, and they come in different colors and different forms and different shapes. They have to be looked at very carefully. So here, this example shows you a bare soil, green grass and straw, dormant grass, and also unclassified things. And you can see the images at the top, and you can see the process images at the bottom. We were using different type of texture color algorithms, using segmentation techniques, using edging techniques, edge detection techniques. And also we had to, more importantly, check them against the manual measurement. That was kind of interesting. We hired several students, manually looked at them, and then count of course, in a very small image segment, count the number of straws, count the number of grass, and then per square area, and then write that down. And then we were basically literally checking that against the image-based values. That was a tedious work, especially for the students. So exposed soil and straw, dormant vegetation, and green vegetation images, example images can be seen here. And for the same images, you can see how our calculated coverage coming from the image-based analysis -AI system is comparing with the manual measurements. Very good measurements were retained, so we were happy, and then that helped us to use this methodology for our project. And we have still been using for the third project right now, so giving us very, very good values. And every time we go back and then do some manual checks, because now we feel comfortable that the algorithm works. So field and greenhouse applications. So you can see we conducted 2 field studies and size 15 test plots in each of them, total of 30 test plots, and then sizes of test plots are given. We focused on the first flush because that was significant. We had sediment bags. You can see some of them at the bottom. We collected these sediments in those bags in several layers and several locations. So we tried to capture the sediment amount that's eroded from the material. And we looked at different growing seasons. Rainfall characteristics are also given here, mean maximum and mean values. In the greenhouse studies, we had 27 different mesocosms, and then their sizes are given. And we had a rainfall simulator, and we also used simulated rainfall with the right concentrations of different elements in it. I'm working with Professor Alan Davis in our environmental engineering, and he's an expert on stormwater. He has been doing this almost for 30 years, so a lot of expertise comes in this project. And then other simulated storms, different types of conditions during the storms are given at the bottom. So here we are looking at, what are we looking at these systems? Field and lab, ground cover, I already mentioned that, volume, sediment, and we collect TSS, total suspended solids. We looked at nitrogen and different type of nitrogen, nitrates, nitrites, and ammonium and organic nitrogen, and also phosphorus, dissolved organic phosphorus, particulate phosphorus, and phosphates. So we are measuring all of those, and we have been doing it for the last several years. Green waste, which is the leaf compost, topsoil and biosolids compost images are shown here. What we did in the lab and in the field in this particular study is use the volume ratio of 2:1 green waste to topsoil, and same ratio for the biosolids. And then they are listed here. And then if you want to kind of understand what they would correspond to by weight, that would be, the first one would be about 29% by weight leaf compost, and the other one would be 9% by weight biosolids compost. And we added the seeds for vegetation, and we added the fertilizer to the topsoil. The nitrogen, phosphorus, and potassium ratio of that fertilizer is given. Of course, we don't have the fertilizer for the other one, and we also had straw for the topsoil only. And properties of these organic matter content, potassium chloride, extracted nitrogen, Melich 3 extraction method for the phosphorus, and then to determine the phosphorus in that way are also listed here. No need to go into all the details, but you can clearly see that there's a lot of phosphorus in the systems. Let me clarify these things. TS is topsoil with straw, and BNS means biosolids compost with no straw. N stands with no, so S stands with straw. And you can clearly see that there's a lot of nitrogen and phosphorus, especially in the compost and compost amanda systems. Let's look at the field ground cover. Ground cover means vegetative growth, developed by, measured by the image-based system. You can clearly see that there is, in the first site, which is the Hanover, Maryland, there's a greater growth with the compost, B, biosolids compost, and in the upper Marlboro, there was slightly higher growth with the topsoil compost. However, when we go to the second growth cycle, they kind of changed. And then when we go to the third cycle by time, they were providing us the similar growth values. So if one is looking at the earlier establishment, that may make a difference, but later down the road, they will probably give you comparable growth values. Discussion here. on how the rainfall impacts works. So once the rainfall affects the soil, there's going to be a soil splash and compaction. So here there's going to be entrainment of the soil particles, and then soil particles will reorganized, and there will be soil sealing. That means especially under the compost or compost amended layer, if there is any type of soil, that soil may be sealed or its hydraulic conductivity can be decreased. And as a result of that, especially if we are not using the compost, especially if we are using tighter materials, that soil sealing will be more obvious. That will lead to a reduced infiltration, and as a result of that, that will be leading to an increased sediment runoff. So that's what you would see in natural systems without the use of compost. So if we add the compost or straw, and that we have seen clearly in our research, that decreases the soil sealing, that increases the infiltration, and that also limits the runoff. That was a big advantage to these natural systems. Here, the straw and compost addition, generates the kinetic energy interception, and then it increases the aggregation, especially with the compost addition. If you look at the compost only, how it affects, compost increases the soil organic, which leads to improved soil aggregation, and then naturally resist the fragmentation, and then scarring. And this basically comes from two parts in the compost. One could be the microbial part, polysaccharides creating bonding bridges between the particles. And also it may come from the organic polymers, organic elements, that like cementing the micro aggregates and the smaller soil particles together. And here with the same straw and compost addition, you also see increased surface roughness and moisture holding capacity. I talked about that during the geotechnical properties, especially with the unsaturated testing, if you remember. Increased saturated hydraulic conductivity. Again, I talked about that when I discussed the KSAT results. Increased field and saturated volumetric water content. And we have also seen that in the laboratory. So that was nice to see the same things in the field, or at least try to relate to field observations. Both straw and compost increase the total volume of the material can hold. This is probably, we are thinking that straw addition creates like a second funnel layer of storage, and compost, as we mentioned before, increases the high moisture fill capacity and larger funnel than what you would obtain with a topsoil. And straw, as we mentioned, higher flow resistance, so the kind of elements to limit the runoff as well. In terms of ground cover, addition of the straw layer helps. This is basically helping in three roles, providing three roles. One of them is the extra water storage, which kind of ties to the slides that I just mentioned, is the topics that I mentioned in the earlier slides, like 2 slides back. This is good for the plant uptake. Protection from the solar energy, that's because it's a physical barrier to evaporation. And then also a temperature layer, and then offering a layer of insulation. Obviously, that doesn't affect much in the greenhouse studies, because in the greenhouse, the temperature is pretty constant, but that helps significantly in field studies, especially in dormant seasons. We also, and I'm not going to provide the results here because we have limited time, but we try to quantify them by Manning's equation. We modify the Manning's equation for the straw condition. We basically play with the N value in the Manning's equation, and that helped us to explain how the straw addition will help to change the velocity conditions. Also, we looked at the hydraulic conductivity using Geoenvironmental model, and then we also explained how the infiltration and then later on the hydraulic conductivity will be affected by the addition of compost. And the results here is straw affects flow resistance, provides flow resistance via Manning's equation, as we said, through the N value in the Manning's equation. And that is based on the stem diameter and number of stems per unit area. So that was nice to be able to apply that. Compost increases infiltration. That was evident from the Geoenvironmental model. And as I mentioned before, compost increase provides sorry about that, provides higher infiltration, that was related to porosity. Recently, we measured the porosity values in the field. What we did is basically we collected samples and we did vacuum saturation in the lab. And then that gave us roughly a porosity of 38% for the compost, 44% for the topsoil, and blend was 61%. So that was a nice one too. So ground cover and sediment values are shown here. Here, the nose straw is brown, and with the straw is yellow. You can clearly see that higher establishment was ground cover, or vegetative growth was established by the straw inclusion, and sediment export or sediment transport was also decreased as a result of that. P, which is the phosphorus export, was reduced by 66 to 99% with the straw addition. Probably 99 would be very high, but roughly around like on an average of 80%. And nitrogen export was also reduced by the straw addition significantly. So that these were nice things, and I explained the theory behind them, or probable theory behind them in earlier slides. So the image-based tool works very well. So we are very happy with that, and then can measure the ground cover data. And field and greenhouse observations, initial grass establishment or vegetative establishment coincided with the greatest flush of nutrients and sediments, which is understandable. Higher the nutrients, you will have higher the growth. But that could also be a potential problem down the road. All treatment coverage, sediment, and nutrient export became similar because the vegetative growth was comparable in the long run. Straw mulching was highly beneficial. Compost treatments with straw performed even better. And benefits from these were obvious. I did not show you the slope ratios, but at steep slope ratios, this was more obvious as compared to shallower slopes, which was even better because nowadays we try to have higher slope ratios in several of the highway systems. And if I have time, I would like to add a few more things on a new project, NCHR. It's not a new project, but I can't really talk a lot about this because we are not finalized with the project. So I can also mention what we are doing. Same project in the field. We are trying to reduce the runoff, establish the water quality, and improve the water quality, and look at the vegetation establishment. And this kind of funny image on the right comes from Federal Highway. So one day, hopefully, we're looking highways like this one. So study site descriptions. So these are the pictures of the mesocosms in the greenhouse field studies. This is the site on exit 38 on I-95, which is basically Highway 32. We had a site here many years ago, conducted a study. So we basically adopted that because we had the instrumentation. You can see at the bottom right, what we are imagining is there is already an existing topsoil layer, what's also called a vegetative or vegetated filter strip. And on top of that, we are placing our compost or compost amended layer, which is basically called a vegetative compost blanket. So the top layer is the blanket. Here, we are using leaf compost only because the local agency was not interested in seeing the biosolids compost in the highway. So this is the location, site before, and compost was added to the site. And this is the piping system on the right. You can see basically to collect the drainage, and then it goes to a box where we take the measurements. And this is basically the right after the construction, how this layer looks like. And this is the area. So this is the schematic diagram of different type of test setups in the location. We have a 10 feet long, 3-inch tank, and 3-inch would be about 7.5 centimeter, and foot would be 10 foot would be about 3 meters. And then other ones also listed here. So we have the compost at different thicknesses and compost at different lengths. And of course, we have a control system here too. and then we are collecting the stormwater runoff originating from the highway. Here, this is the established system, and after the vegetative growth in August 2020, nothing much changed after that. So we're still taking measurements. So now 2021 versus 2020 would be essentially similar in terms of look, even though we are collecting a lot of samples, not only water samples, but also soil samples from the site. And this is the setups, different setups in the greenhouse. We have different slope ratios, different compost depths, drainage areas, and the underlying soil. So here, this is the blanket right under the grass, and there is also a soil that's not shown within the under the vegetative compost blanket. That could be sandy, that could be clay. So we vary and play with those, even though typically in the field those layers would be sandy. Range of different rainfall intensities, and then volumes and durations, and then we water them on a regular basis, and then we do lots of different measurements, including the image-based ground cover measurements and so on and so forth. So in the field, different than the lab, we are also doing hydrological analysis. We are taking air temperatures, evapotranspiration. We are measuring those, and these ET rates we are measuring in the field, and then we are using them for calculating the storage. So you can see some of the observed and estimated storage values based on these hydrological measurements. We're happy with those measurements so far. We have still some questions about storage that we calculated as opposed to the storage that we observe in the field, but again, I'm not going to go into details right now. Here, the idea is to come up with the performance curves. So, for instance, X inches of rainfall capture for Y feet of compost layer or vegetative compost blanket layer per traffic lane. Those type of curves we believe will be very useful to practicing engineers. Water quality analysis. We are looking at the nutrients. That's important. One of them is the total suspended solids. TSS values decrease significantly. You can see the values in the inflow, and then you can see the values originating from the blankets. They kind of, come to an equilibrium after some time, but it takes time. Here, the nitrogen values in the field are, and as well as in the greenhouse values are high, especially in the field. You can see the nitrogen values are here, median and in the inflow and outflow are shown here, so significant difference. And then same thing is true for the greenhouse values. Inflow and outflow values are different. Recommended EPA recommended values are very low, so that is a flag, raised flag. Basically, here the nitrogen nutrient concentrations can be problematic for the compost, as some others also mentioned in the past. Phosphorus, same thing, and no need to continue, same thing, but again, we have some concerns with the phosphorus as well, and we have to be, we will be looking into that. So compost leaches large concentrations, but these concentrations decrease to levels, but may not decrease to acceptable levels after some time. And let me continue with those things. I already mentioned about the water quality, results on water quality, and TSS, we have some reduction, and nitrogen and phosphorus, we have leaching, and then obviously the compost type will impact all these things. So as a result, for the slope stabilization or for slope applications, it may be okay. For the nutrient discharge, I think we have to be somewhat careful about these systems. What we are doing right now is in the lab, we are also looking at these systems in a more advanced, more focused way. So on the right side, you can see the topsoil at the bottom, vegetative filter strip, and compost blanket at the top. So we are collecting samples like those from the field, and we'll be running nutrient leaching and absorption tests to see how much of those nutrients like nitrogen and phosphorus is really absorbed on these topsoils, and perhaps even in the subgrade, and probably they will be captured in the subsoil. And then we'll be looking at this denitrification and volatilization of the nitrogen, as well as the transport and sorption of the of that, and also the phosphorus, same thing in the field. We are also looking at water quality mass balance through a model, numerical model, and then we would like to see actually how that transport would be. Krishna, do I have time or should I stop here?
Go ahead.
Okay, I have a few more things to say about another project. In this project, we were interested in looking at the compost geotextile hydraulic compatibility. And that is not related to the project that you have seen, but we were funded by Geosynthetic Institute on this to look at landfill cover applications. In the landfill cover applications like this, we have a surface layer, and that surface layer is typically a topsoil. Now, we have the expertise on these compost systems to replace its topsoil. So we wanted to bring our expertise to this business. In the landfill cover systems, there's also a protection layer. So we wanted to see is compost is a superior vegetative facilitation material. We have already seen that in other projects, and a good erosion control material. And if it is, and we have also seen that in earlier projects, but is that going to be compatible with any type of textiles placed right between the systems where the surface layer or protection layer is overlying on a drainage layer, a textile, for instance. Obviously, this drainage layer could come in different forms. Sometimes people can use geocomposites. Geocomposites will still have textiles in it. So the compatibility with the textile is quite important. Sometimes we have seen that there's no protection layer. That surface layer is directly sitting on the drainage layer. So there are different scenarios. So we looked at the soil, different types of compost here. Two composts, again, the green waste and biosolids compost. We also include the protective cover material, more gravelly, sandy, gravelly soil. And also our topsoil was the control material. You can see the fines contents ranges, and you can also see the organic matter content ranges. What we did is we ran long-term filtration tests in columns in which we placed the compost and sometimes compost plus protective layers sitting on a textile. And then we ran tests in the systems. These are constant head hydraulic conductivity runs. However, one has to be careful that you need to use a deaeration system, because oxygen contents inside the tap water can be quite problematic when you are running any type of clogging test with the textiles, because of the air bubbles sitting on or inside the textile or around the textile can basically skew the values. So therefore, a system that allows the continuous deairing of the water is required. One of the results among the several is on a woven geotextile. Here you can see a very good permeability ratios. Permeability ratio 1 basically indicates that the system is compatible. People typically recommend permeability ratios less than 3. The reason why is 3 is a safety factor. And if you are using non-woven geotextiles, you can experience a little more clogging in the systems, but again, within an acceptable level. We ran some we have image analysis tools developed earlier to analyze the textiles. You can see the textile on the left, the virgin textile before the test. You can see the woven geotextile after the test. There are small changes in the pore sizes, which can be measured by our systems. We are also running permittivity tests on the post-test geotextiles, and then making sure that the image-based values are comparable with the permittivity test-based values, and they were. And non-woven geotextile requires sectioning. Like if you ever dealt with the scientists in geology, they do sectioning, a thin sectioning of rocks. So you would do the same thing for textiles, or you need to do that because otherwise you can't see inside the textile. So we have this epoxy resin impregnation and a series of cutting, grinding, lapping, and polishing techniques that we apply to textiles. We take planar as well as cross sections, and then we take images of those, and then we basically bring them together to come up with the 3-dimensional view of a textile. And you can see one of the textile images images here where you can see the entrapped soil particles that helps us just for, qualitative observation. Then we can quantify these to come up with the pore size distributions. For instance, if you look at the non-wovens, you can see the black line, dark black line is the pore size distribution of the virgin geotextile. And then you can see the non-woven geotextile, and you can see how the pore size distribution differs as a result of filtration. And in terms of wovens, obviously these changes is less dramatic, right? You can see the virgin one here, and you can see the changes in the woven geotextile, less dramatic because woven geotextiles have uniform pore sizes, and they don't have the third dimension. I wanted to, briefly mention about this study. This study continued about 1.5 years. So what I'm basically doing here is giving you a synopsis of that study. What we figured out is the current existing filter criteria that's applicable for natural earthen material is not necessarily applicable for these recycled materials. And I have seen that in my other studies as well. Inclusion of a protective cover beneath the compost layer decreases the clogging potential, but on the other hand can promote the piping because of its high hydraulic conductivity. Compost geotextile combinations performed well. They were within the filtration criteria. Permeability ratios were less than 1. Percent open area ratio, POA, is basically the ratio of the percent open area of the woven geotextile before and after the test. And permittivity ratio, psi-R, would be a permittivity of the comparison of the permittivity of the textile before and after the test. So they were in very good range, around 1. That indicates that the flow performance of the textile was not affected significantly upon filtration. Compost geotextile and topsoil geotextile combinations in general gave acceptable filtration. So now we are looking at these systems in the greenhouse again. You can see the top studies. We have these data loggers, and we have the sensors to measure the tensiometers and volumetric water content sensors to provide measurements at different depths. We also have a textile at the bottom here. We are not running filtration tests, but we are basically will be looking at the performance of the textile upon completion of these tests. Here, I would like to acknowledge my colleagues. Dr. Alan Davis, an environmental engineer from our department. Gary Felton is a soil scientist. John Lee Cox is a plant scientist. And this project was supported by several agencies and then listed here. So I need to thank all the students who helped in this project. Without their effort, we wouldn't be able to materialize all these things. So I appreciate the help of everybody. And again, I also thank Krishna for organizing this seminar one more time, and thank you everybody for attending.